Assalamu alaikum dear students. Bismillahir Rahmanir Rahim. Welcome you in lecture 4, and inshallah in this lecture you will see the analysis of an overhang beam with a different type of loading. Okay, so this is the example. Inshallah we will do this example clear, and you will see that there is a support at A, and similarly there is a support at C, and there is linearly varying loads, and there is a UDL which is acting in upward direction. So let's see how we will assign a linearly varying load and a UDL load. Clear? Before going to analyze the structure, okay, I want to mention you I want to explain basically the V22, because in previous lecture I don't explain V22. Clear? Although I explain M33, but I don't explain this one. Okay, I forget it. So therefore you must know, as I already mentioned you in lecture 3, that V33 means basically you need to understand the axis. Okay, this is the global axis of SAF. Okay, 2000. Clear? SAF basically denote x-axis with a uh, with 1 1. Similarly, z-axis it is denoted by with 2 2. Okay, and y-axis is denoted by 3 3. Clear? So it is a kind of different type of it is a kind of different type of a representation. Okay, representation of axis basically. So now your axis will be like in this way. Now your axis will be this is axis 1 1. Clear? And now it will represent 1, it will represent 3, and it will represent 2. So whenever, for example, if you draw a beam section, clear, if it is a beam 3D view, okay, if it is a beam 3D view and there is the reaction, okay, so let's say, for example, if I place the axis right there, okay, so 1 will be represent the line, the length of the beam, 2 will be represent the depth of the beam. Clear? Depth of the beam will be represented by 2. Clear? And y will represent the thickness of, that is the width of the beam, that is 3, and 1 will represent the length of the beam. Clear? So basically shear means what? As if you revisit the definition of shear, and in mechanics of structure by R.C. Hebler, so you will see that they divide basically the beam into some planes. Okay, let's say these are the horizontal planes. You assume that the beam is consisting of thinner planes. Okay, thinner planes, and similarly the beam is also assumed it is consist of vertical planes. Clear? When they are basically deriving the, I think so, the shear formula, so basically they assume that the beam is consisting of thinner planes, both in vertical and horizontal direction. Clear? So this is continued. Okay, now once you applied a load to a beam, so this load trying to split these planes, let's say you assume that the beam is consist of planes, okay, of wooden planes, and they are placed over each other. So if, if these are planes, clear, these are planes, and they are just kept over each other, there is no glue in between these two planes, okay. So if you apply the load, you will see that your planes will be will slip, okay, over each other, clear, they will slip over each other, clear, and it will make some kind of you know displacement, or some kind of, you can say, this will go upward, clear, and this will go, okay, the length of the lower one will be reduced, okay, it will bend like in this shape, clear, and similarly if you look to the above one, there will be somewhat there, clear. So due to this slipping, why they slip? Because there is no bond, there is no bond forces exist in between these planes, okay, they are you can say they are split and just dump over each other. Now due to this kind of slipping, this kind of slipping along the planes with each other is called shear, okay, this is called basically shear. So now this is horizontal shear, clear, and as this shear occurred in x direction, like in direction 1 1, so basically it is represented by axial force. In SAP it is represented by axial force. You can say it that this is V11, clear, this is, you can say that this is V11. Similarly the planes which is in perpendicular direction, which is in vertical direction, they also tends to move in upward and downward direction. The planes which is right near the supports of beam, and the planes which is somewhat far away from the supports, there is different types of movement, okay. the the planes which is near the support, they are trying to move in upward direction, while the planes which is far away from the supports, they are trying to move in downward direction. So therefore the plane which is vertical, okay, they move in downward direction, but the planes which is near the supports, they're trying to move in upward direction, okay. So if we assume that there will be no bond forces exist in between these planes, so the movement will be somewhat like this, okay. So there is a kind of force, and due to that force these planes move, and that force is basically called the shear force. Now you see that these planes, the movement of these planes will be more along the supports, while minimum at near the mid portion, okay, because shear is minimum at the mid portion, so therefore this movement will be maximum at supports, clear. Now you can see that if you compare this movement with your x-axis, that is 1, that is 2, and that is 3, so you can see this movement is basically along the 2 axis, this is basically along z axis. So therefore we calculate shear along 2 okay, we basically calculate shear along 2 and if these planes move in this direction, okay, they either move in this direction or either move in this direction, so then they will be, we will calculate shear about 3 axis. If there is any kind of movements in between these planes in along the 3, or you can say along the y axis, so that will be calculated as V33. So I think this is clear right now, okay, this is enough. Now we comes to to the example, okay, that how we can solve this example. Clear? We need first of all to check the units, that is kilonewton and meter. So from this kernel units you will select the appropriate units, okay, that is kilonewton meter. Then you need to bring new model, that is beam, okay. Whatever the values will be, you just need to check this button and edit, okay. You need to check the units, okay, and then select spacing. Clear? So if you look to the example, in this example basically you see that this is support A and this is support C. So SAP basically, you can change these names in SAP as well, okay. Here this is possible, you change this, that support, this is my support A and this is my support C and this is my support the free end, that is D. Clear? So you can change these as well, but leaving this at their own place, okay. And we will just move that the B is located right below the point and we ignore C. So AB is our first span, and that is 1 plus 3, that is equals to 4. Clear? This is 4 meter. Clear? And then the next span is basically start from B. Clear? The next span is basically start from this is my support A and this is my support B, okay, and this is my support C. So you see that A starts to B, okay, that is 4 meter, and now this is my first span. Spacing, so the spacing in between A and B is 4 meter. Now the spacing in between B and C is clear, that is 2 plus 7 plus 1 plus 1, that comes out to be 4 meter. Clear? So spacing will be, the next spacing will also be equals to 4 meter. Clear? Sorry, 3 meter, that is 3 meter, that is 3 meter. 2 plus 1, this is the support. Clear? So here is support. Clear? So this is 3 meter. Clear? And okay. Clear? Remove this one, and you see this, okay, you see these coordinate axes. Clear? This is very important. You see that x-axis, this is positive global axis. Clear? This is positive global axis. Now you see the positive global axis, which is x-axis along the length, z-axis along the depth, and y-axis along the width of the section. Okay, so you need to adjust exit plane. Clear? And from A to B we have 4 meter, and from B to C we have 3 meter. So first of all, the second step is that we have to select the proper joints. Okay, now if we come to the example, we see that there is a support and there is a support. One thing must be remember, okay, one thing must be kept in mind. Basically there is no support here. Clear? So there is no support. This is the sign of this arrow shape is the sign of simply support. Okay, so you can place here a hinge, okay, and you can place here a ruler. Clear? Or you can place here a hinge, and here you can place a ruler support. It doesn't matter. Okay, you can replace these supports, it doesn't matter. Okay, in case of simply support. Okay, so basically now we need to remove this one. So just click on the support and assign joint and restraint. Clear? And just select this. Okay, this is a special joint. Okay, this is a special kind of joint. Okay, so this is a joint at which we have no support here. Clear? Reaction is here. Okay, so this will be a ruler. So check it whether it is ruler or not. So there is no reaction assigned to this ruler. Okay, so assign it as a ruler support. Clear? So okay, also check it, assign joint strand, and this is hinge, so you can select hinge. Okay, and okay. Now after assigning the joints, we will assign the loading. Clear? So here we can see that this is uniformly distributed load. Clear? So this is uniformly distributed load, and you see that at this point basically we have this is basically once we select this span, okay, so our 0 starts from A. Clear? Our 0 starts from A. So in absolute spacing we will just insert 0. At 0 we have 0 loading. Clear? We have 0 loading, and at a distance of 3 meter from A, okay, at a distance 3 meter from A, you see that we have a loading of 8 kilonewton. Okay, now you see that at a distance of 3 further, at a distance of 3 we have you see that we have no loading. At this point 3 toward this point we have no loading, so we will insert 0. Clear? This is necessary, because if you don't put this value, these two values, okay, your safe will assume that this 8 kilonewton load is basically through this span. Clear? So they will assume it like this. So you must need to insert this at this point you have to insert two values. Okay, at 3 you have one value is 8 kilonewton, which is to the left. Okay, and at 3 which is you have 0 value which is to the right. Clear? So let's see, we will select the span. Clear? Assign frame loads, distribute it. Okay, you need to close this multiplier, that is 0. Clear? Modify. Okay, now you have a gravity load. Okay, you have a gravity load. Press this button, kilonewton meter. Clear? And now you will use absolute distances. So I already mentioned you that at 0 you have 0 loading, and at a distance 3 meter, okay, at a distance 3 meter you have a loading of 8 kilonewton per meter. Clear? So 8 kilonewton per meter. Clear? And then again to the right side at 3 equals to 0. So this is the loading. Clear? And then we need to assign loading to this span. So at this span you see the loading starts from at 1 meter, at a 1 meter, and to the rest of the span. Okay, for a distance of 3 meter. So basically we select it. Now the 0 is now start from this point. Clear? The 0 is basically start from, okay, once you are making separate selection of span, your 0 will be changes. Clear? Your 0 will be changes. Now this is the support. Now your 0 starts from this point. Clear? And the distance is measured in a positive way. This point is basically now at a distance of 3 meter. So to assign this UDL, it should be remembered that this is in upward direction, not in the direction of gravity. So you need to compare this loading with your axis. Clear? With your axis. This is your z axis. Clear? This is your z axis, this is your y axis, and this is your x axis. Clear? So this load is basically acting in the z direction. So therefore we remove the gravity and we select z axis. That means basically to apply the load in the direction of z axis. If this load is basically for example, if this load is acting in downward direction, so I can use it the option gravity, as well as I will use it Z axis. So let's see, this load is basically acting in upward direction. So it starts from a distance of 1 meter. So therefore here basically if I want to insert my values at 0, I don't start from 0. Clear? I don't start from 0 because my loading is starting from 1. So therefore I insert 1. At 1 I have a value of 4 kilonewton, and then okay, it's at 3 meter, not at 2 meter. Clear? Because the distance is measured from this point. Clear? So at a distance 3 I have a loading of 4. Clear? So let's see, I select this pen, assign frame loading and distribute it. Clear? So check the units, this option, global, okay, gravity. Now you have to apply the load in Z direction, not in gravity direction. Okay, and there you can select absolute, you make it equals to 0. Clear? That is the all loading. Clear? And now at a distance of 1 meter from support B, you have a loading intensity of 4 kilonewton, and up to a distance of 3 meter, okay, you have a loading intensity of 4 kilonewton. Clear? And the rest is 0. Clear? So this is a kind of loading. Clear? Now the loading is assigned, the joints are assigned, you can now analyze. So here you can say model allow run analysis, F5 or run analysis. Clear? So model do not run, okay, and run analysis right now. You need to save it, okay. That is you can say overhang with a linear load, okay, linear load. Clicking. Okay, so this is your analysis is done. Now you need to first of all check your reaction. So just press this button and select joint and here and okay. So these are your joint reaction, which is 10 kilonewton and 6 kilonewton. You can see 10 kilonewton and 6 kilonewton. So our reactions are okay. Once your reactions are okay, your shear and moment diagram will obviously be, that will be okay. Clear? So this is our shear diagram. Let's see, check it. Press this button, frames, okay, and you select shear 2. I explained this point. Clear? And you need values, okay. So this is your shear diagram, okay. That is just similar to the to this one. Clear? 10, 2, 8. Clear? So that is 10, 2 and 8. Clear? You must remember that basically it draw a shear diagram in a different way. Clear? You don't need to be confused that this portion is positive here and this portion is negative here, but in SAP this portion is negative and this, it doesn't matter. Clear? It doesn't matter. The next is bending moment diagram. So select it and frames, okay, and moment about 3. Clear? And okay. So this is your moment diagram, which is totally, you can say, negative diagram. Clear? Negative bending moment 18 and 16. Let's see, check it. This one 18 and 16. Clear? So this is a kind of analysis which we make for an overhang beam having a linearly varying load with a point load. In next lecture, inshallah, we're trying to bring some sort of different loading. Clear? So if you have any question, okay, if you have any doubts, okay, or any suggestions, you can contact me and watch the videos and enjoy. Thank you.